Thank you. So thank you all very much for coming. Big thank you for the invitation and opportunity to speak, and also for hosting me. I've been having a really nice time here. So as Hong said, the title is a bit long, so kind of shorter version is finding rainbow cycles in graphs with some amount of average degrees. And I also want to mention some kind of nice connections between that problem and additive number theory. So everything I'm going to say is joint work with Noga Alon, Liza Zarman, Dima Zaharov, and Or Zamir. So let me start slowly. So first, kind of initial question here that is happening in the background. So what is a general Turan question asking? So you are asking how many edges do you need to have in a graph in order to guarantee some kind of structure, right? So that's the, usually if the structure is a graph, you refer to this as the Turan problem and the Turan number, but there are a lot of different variations. So let me mention one that is very often taught in one of the first classes on graph theory. It's a very simple question, which asks how many edges you need in a graph to guarantee a cycle. And anyone wants to volunteer an answer, and I promise it's not a trick question. N. Yeah, thank you. The answer is N, because as soon as you have n edges, you are not a forest. The forest with the maximum number of edges is a spanning tree, it has n minus 1. So that's a kind of basic thing you teach in graph theory course when you teach people what is a tree, what's a path, what's a cycle. And it's also something that if you're looking for this type of objects, it kind of pops up quite a bit. So it's a very simple thing, but you kind of use it without thinking very often. That it's a very basic kind of relatively omnipresent statement when you work with this type of things. So very good. So we are going to extend this problem in a certain way, but in order to do that, I need to kind of introduce a slightly different perspective, or well, somewhat different direction in which you can generalize Turan problems. And this will be so-called rainbow Turan problems. But so let me start by defining what I mean by a rainbow coloring. So an edge color graph and all my colorings in this talk are going to be edge colorings, so I might not be writing it from now on, but I'll try. So an edge colored graph is said to be rainbow if all its edges have different colors. And the reason this was introduced is because it actually pops up quite naturally for a variety of problems that you can kind of reduce. And in addition to just being interested in what density in a graph you need to guarantee something, you kind of sometimes actually want to find this type of rainbow object. And so, for example, they pop up in this famous whole page conjecture in group theory, also Reiser-Broaldi-Stein, where there is some exciting results coming out by Richard soon, so maybe he'll tell you something about it when he visits. I saw him on the board. So there is a lot of problems where actually these rainbow structures pop up quite naturally. But I really like to think of it as, in some sense, the contrary problem to Ramsey problems. So when you think about Ramsey, what you're trying to do is, in some kind of large structure, find some kind of structure, some nice, well-organized substructure. And when you're looking for rainbow objects, instead of finding these nice places in your graph, you're actually looking for the most chaotic places you can, right? So if you think of a graph with big clique, which is colored using R colors or however many, the Ramsey now wants to find a monochromatic clique. And if you want to find a rainbow one, this is kind of the complete opposite of the completely monochromatic one. So unfortunately, unlike in Ramsey, where the whole point of Ramsey theory is that in a large enough structure, you can always guarantee nice places that, like, there you cannot have complete chaos. For rainbow, it's not true. So it's not true that in any structure you can find chaotic places. And the reason is that your whole thing could just be monochromatic, could be already extremely structured. What you start with, you're not going to find any chaos unless you have some amount of assumption and some amount of understanding on top. And so one assumption that pops up in many of these applications that I mentioned, and that has been studied in its own right because it's a very natural concept that pops up quite a bit, is to assume that the graph you're looking at is properly colored. So proper edge coloring graph is a coloring where every vertex is incident to edges of the only different colors. Okay, so in other words, the star spanned at the vertex is rainbow. So in some sense, what's going on here is I'm assuming some kind of weak local chaotic assumption on my coloring. So I'm going to assume that my underlying graph is properly colored, and I'm going to look for rainbow objects. So that's kind of the topic that we're getting at and that we will look at, and that was introduced by Keevash, Mubayi, Sudakov and Verstraëte. But the real kind of picture that is going on in the background is you assume some kind of local weak chaos assumption on your graph. At every vertex you have a rainbow picture. It's not structured, it's not completely in one. I mean, and you can also weaken this a bit in various ways, but let's not go into that. And the question is then, can you, with this simple local assumption that happens around every vertex, can you somehow lift it to actually build some kind of larger, more complicated, more interesting rainbow structures in your whole graph? So that's the question that we are going to look at. So let me write a kind of general one. And this was kind of codified by Keevash, by Sudakov, Verstraëte. In 2006. So the question that they ask is, how many edges do you need in an n-vertex graph so that in any proper edge coloring you can find a rainbow copy of some structure. So this is referred to as the rainbow-to-run problem. So whatever structure you can think of and look for in the usual to-run world, you can ask exactly the same question here. And sometimes it's a very interesting problem. So they raise quite a few in this paper from 2006. And the specific one that I want to focus on today is actually just a variant of this easy thing that I started with. So how many edges do you need to have in a graph so that if you look at the proper coloring, you are guaranteed a rainbow cycle? So you have a YP. Good. So let me just here change it because this is the only version of this problem that I'm going to talk about today. But I just wanted to say that you can ask this question in more generality and various interesting things pop up. So they were motivated actually also by certain applications from additive number theory when they asked this. but that was for a different instance of this rainbow to run problem than the one I'm going to talk about. But they raised this question about the rainbow cycle explicitly because it's somehow nice, and because the graph version, the normal to run version, is so easy that somehow it seems completely ridiculous that this one turns out to be quite a bit not, well, seems at least you need to do something clever. It attracted a lot of attention and has been improved quite a bit over the years. So let me tell you what is known about this problem. So actually I have another board here, but maybe I should not use it. This is a combinatorial problem in its own right. I'll use the board. Anyway, so the first question that comes to mind is, are the problems actually the same? Is the answer the same? And does anyone who didn't write a paper on this know what the answer is? So do you have some lower bound maybe which can show that the answer needs to be different, bigger than n? Perfect, yes. So let me start with lower bounds. Actually, I forgot. I want to define what's that. Let's denote by Ex star and C the answer. So this is just going to be my rainbow to run number on n vertices of the family of all cycles. So if you wish, it's just the answer to that question, but it's a kind of an instance of a more general problem. So now what about lower bounds? Precisely as you said, if you take the hypercube graph and you color each direction in a different color, that guarantees you will not have a rainbow. So that's a proper coloring to start with. You will not have a rainbow cycle, because as soon as you move in a direction on a hypercube, at some point after you walk in this layer, you need to go back, and that will reuse the same color. And you will get roughly n log n over 2 edges. So the first lower bound is that this Ex star and C is at least, and let me put here a roughly tweak, 1/2 n log base 2n. And this twiddly thing is here simply because there should be some floors, or this is precisely a lower bound if n is a power of 2, and so on. So let me draw a picture just to illustrate. So you can formally define it by, and explain this by hypercube being a binary sequences of length log 2n, and then their two vertices are adjacent if they differ in one coordinate, and then this coordinate gives you the coloring. But I think kind of the picture tells you most of the story, and since we're not going to really focus so much on the lower bounds, this is just for completeness and to show that actually the answers are different. So this is this is a 3D hypercube, and you color each direction in a different color, and then if you added a fourth one, you just copy this and you put the matching in the fourth color between, and so on. So whenever you move along the red edge, you are stuck in the top part until you reuse an edge to go back. So that's really what's going on with this lower bound. So there is a better one due to Keevash, Mubayi, Sudakov and Verstraëte, which is still the best known lower bound as far as I'm aware, which gives something like 3 over log base 2 of 6 times log base 2 of n, which is just 3 times log base 6 of n, but I wanted to write it in the, so that, and I'm missing an n, and I'm missing a, so actually let me already do the bit that where I add this 2 over n. So now I'm talking about the average degree that you need here. And I'm doing this because the average degree is really what is controlling the answer to this problem, and it kind of makes it nicer for you to compare what is actually the answer. So I'll mostly be talking about this expression. So this is right, twice the number of edges divided by number of vertices, that's just the average degree. And this is because log 2 of 8 is 3, so this is a bit bigger than 1, so you're kind of improving by a constant factor by a tiny bit. And this comes from a certain kind of Cayley blow-up construction. They didn't actually define it that way, but it comes from this additive perspective on this problem that I'm going to tell you a little bit about soon. Very good, so these are the lower bounds. So now, what about the upper bounds? So as I said, this question attracted quite a bit of attention over the years. So let me put here Keevash, Mubayi, Sudakov, and Verstraëte. So, and C, and again I'm talking about it in this average degree perspective. So what they got in their paper was that this is at most big O of n to the 1/3. So this is again from the original paper from 2006. And this just came because they said, okay, we forbid a single cycle, and then they had bounds for a single forbidden cycle. So they get this as an upper bound. So the first bound that actually exploited the fact that all the cycle lengths are forbidden came about 7 years later. So it gave an upper bound of e to the log n to the power 1/2 plus little of 1. So roughly e to the root log n. And this was by Sudakov, 2013. I think I'm sticking with the archive years rather, because otherwise things get a bit confusing soon. But yeah, so don't hold me too much on the years. They should be roughly correct. So very good. So that says that the answer is actually subpolynomial, but it's not quite there to being polylogarithmic, and the best lower bound is right just log times some constant. So the kind of big breakthrough here was then achieved by Janzer, who got constant times log to the 4n. And this is a really, really nice paper. It was a paper which introduced his homomorphism counting approach, which then later he used for quite a few other things that and to prove very nice stuff. So also I should say that this paper introduced this pass to expander approach on this at least question, and so these are two very different kind of methods that people looked at. So let me underline this in red, and let me underline this in yellow. So because the following approaches are in some sense then trying to push and modify and extend this, at least on a high level, the idea that were at least introduced in these two first papers, but of course building up quite a few new things, and in some sense developing this two very versatile and nice ideas to attack this problem and many others. So the next paper, which is also nice and which actually was most initially motivated by some geometric problems, and then which kind of are reusing the ideas that Tom István figured out for this rainbow cycle instance, just somehow a hypergraph variant of this. So this is log 2 plus little of 1 n. So it's log squared n times some power of log n. So this is Tomon, 2021, I think. And so this again went back to the pass to expander approach, and it's actually introducing some very nice new tweaks there, and some of them I'll maybe mention later on when I tell you a little bit about what we are doing. And also some of the ideas here were useful for us for several other recent papers. But following that, there were two independent papers, very nice also, and kind of going back to the other idea, Oliver, which removed this log n. So this was, one of them was by Kim-Lee-Liu-Tran. So I think this was still 2022, maybe December, but maybe you can correct me. And independently, Janzer and Sudakov. And they went back to this homomorphism counting and in some sense did it better, plus some nice regularization ideas. And in some sense, I believe, or at least I, when first looked at this problem, believed that actually the answer might be around log squared n. So this was kind of trying to match this log squared n, which represents a natural barrier for both approaches in some sense. And we'll see that hopefully towards the end of the talk. So somewhat, so the result that I want to talk about today, which is joint work with Noga, Lisa, Dima, and Orr, is that actually the answer is log n to the 1 plus little of 1. So this lower bound is not far from the truth. And actually we get it correct up to a log n factor. So the average degree you need in a graph so that any proper edge coloring of it will guarantee you a rainbow cycle is roughly log n times log n, or that suffices. And there is still the question of whether this log n is necessary here or not. And I'm not sure. I believe both for various durations of time, but currently I think my belief is that I don't know. So there are some reasons why log n might be necessary. On the other hand, there are some reasons why it might not. So it might go either way, I think. So very good. So any questions about the result or anything else? Good. So before telling you a little bit about how we prove this, I want to actually tell you something about a nice connection that we observed while working on this to additive number theory. So I really like this connection and was not really aware of some of the ideas that exist and that people look at there. So let me tell you a bit about that, and then I'll tell you a little bit about the ideas that go into the proof of that. So also, I think in my color coding, I'm supposed to underline our result in red. Because we are going back to the pass to the expander approach. So, very good. So, as I said, in order to tell you a little bit about this additive stuff, I need another definition. So if you're given an abelian group, G with the operation being plus, we say that the subset, say D, let's denote its elements as D1 up to dk of the group is dissociated if you have any non-trivial linear combination of these elements using just plus minus 1 or 0, means that you don't have any non-trivial linear combination of these elements using just plus minus 1 and 0. So k is equal to identity for epsilon I living in plus minus 1 and 0 implies that epsilon I is equal to 0 for all I. So let's just stare at this for a second. So what I'm saying here is something that should be very reminiscent of a definition of linear independence in vector spaces, right? So I'm saying if you have, that you don't have like a set is linearly independent if it doesn't have any non-trivial linear combination. So here we are working in a group, not in a vector space, so you don't have full power of linear independence, but you still can always take a plus minus. Minus just means you take an inverse of it, of this element. So over this set, which sort of plays the role of a field here with quotation marks, this in some sense is playing the same game as linear independence in vector spaces. So it's kind of a poor man's linear, well, the theory of linear algebra when you work with arbitrary groups. So just to make sure we're on the same page, in the abelian world, this plus minus 1, this is actually equivalent to just saying, because you can move the minus 1s to the other side, that all subset sums of this set are different. Right? So if you have any two subset sums which are equal, you can get a non-trivial linear combination. So a set is dissociated if and only if it has all different subset sums. So this is maybe a more natural definition to think about, but on the other hand, this one is the one that actually turns out to be kind of more useful, and the reason and why this was introduced in additive number theory. It was also introduced in harmonic analysis, and it really pops up quite a bit and is a useful concept, and in part because it actually it has some properties that you associate with linearly independent sets and bases, and if you take a maximal one, if you work in vector spaces. So for example, if you take some subset of your group and you take a maximal dissociated subset of it, then this is spanning, right? So you will be able to hit everything in the set. Why? If you don't hit someone, you can add it to your dissociated set. So it captures this spanning property that you have in vector spaces. There is also a nice result which says that these maximal dissociated sets should be similar in size, so they will not all be equal as in vector space. The size of maximal independent subset in a vector space is always equal, and it's called the dimension. Here it's not going to be true, but it's roughly true up to some log factors that I don't want to go into. They will be actually very similar. So it also is very natural to define a notion of dimension here, which was called additive dimension by Shen and Skredov. So let me write this out. So it's just if you are given the subset of your group, then the dimension, and there are multiple notions of dimension in additive number theory. So this is called additive dimension of S is just the maximum size of a dissociated subset. Right, so it kind of recovers this idea of dimension in vector spaces as well. So this definition is due to Shen and Skredov, but it actually was popping up before, just people didn't give it a name and didn't call it a dimension yet. And yeah, there is also a notion of Freiman dimension, which modifies this and allows you to use here not just plus minus 1, but bigger integers. So, but this one is kind of stronger in certain cases. And as far as I understand, well, it was used quite a bit, the idea of dissociated subsets. So, I mean, I'm not an additive number theorist, so I'm not an expert on this, but I looked a bit at what people were doing with this. So, very good. So that's a dimension. So what does this have to do with the rainbow cycle problem? Which, that's a very fair question. So, it turns out that you can use it to get some kind of reasonable control on the dimension of subsets. So in order to explain that, first I need one last piece of notation, which is just that a notion of a sum set, which is another kind of classical object that has been studied quite a lot. So it's just, so for two subsets of your group, A plus B is just the collection of pairwise sums where you take the elements from the respective sets. And this is kind of one of the key concepts that additive number theory studies. And in particular, what people looked at quite a bit is what happens if you have a set which has a small doubling. So suppose that A plus A is small, what can you say about the set A? So this goes back to 1960s and the result of Freiman, which kind of did this when the group is cyclic, and it's a pretty big thing, and in particular what he proved is that if you have small doubling, then you're somewhat similar to a subspace, and or well, you can be covered by some arithmetic progressions is the correct way of saying it, and this turns out to be quite useful when you're studying this subject. So what we are going to do here is we are going to extend the result of Sanders using our rainbow cycle stuff, or I'll also give kind of a different proof of a somewhat weaker bound. So what Sanders proved here is that if size of A plus A is at most, say, k times the size of the set A, then dimension of A is at most big O of k times log the size of A. So k here you can let depend on the size of A. It's just an arbitrary number which you can pick. So in some sense it's telling you that in order to get some control on the dimension of a set, it's very related to how big its subset is. So this is a very nice result, and it's not that hard. It's using Pluneke inequalities, but it is using some amount of Fourier analysis. So, and it also in particular only applies in the abelian case. So everything that I said so far, I was sticking to the abelian world. But actually there is no reason to do that, and there's been quite a lot of work in trying to understand what happens about especially kind of control of sets with small doubling in non-abelian groups. So this was kickstarted by Terry Tao some 15, 20 years ago. And since then, there's been really a lot of work in understanding what you can do with this type of things. And what we prove is that in the non-abelian world, you also have a very similar bound. So let me just quickly change the definition stays exactly the same, except I'm going to remove the word abelian here. I'm going to replace the plus with times, just so you're not confused. So this now becomes arbitrary. Right, so now instead of plus and instead of this, what you're doing is you're just taking products. And this is really just changing the notation to kind of highlight that we are no longer in the abelian world. So everything else here stays exactly the same. So now this is true. Let's put here G abelian. And I mean here instead of A plus B you define A times B, so it's exactly the same notions. Just to stick with a different definition. So now the theorem that, or corollary, let me call it, that we prove, and that kind of comes nicely from this rainbow cycle stuff, is that actually given an arbitrary group, and a finite, say, subset. So here you also need finite subset, but if things are, everything is finite for me, let's say. A of the group such that size of A times A is at most K times the size of A, so it has small doubling, then the dimension of this subset is at most big O of K times log the size of the set times log size of the set itself. So really, what both of these results are saying is that if your set has small doubling, it needs to be structured in a sense, and it needs to be structured in a sense that it has, in some sense, small dimension. You can span it using very few elements of your group by just taking plus minus one linear combination. Very good. So let me quickly show you how the rainbow cycles apply here. And where they come into the picture. It's a nice short proof. And also let me mention that Conlon Fox, Yep Pam and Hoi Pam and Liana Yepremian, so they have a nice result coming on finding Ramsey graphs in arbitrary or random Cayley graphs of arbitrary groups, and they actually needed a lemma which kind of controls, well, it's an asymmetric variant of this, which you get in practically the same way, but they needed to kind of count how many such subsets can you have which have small doubling, and this you can get somewhat weaker bound than what they get and what they need, just because if you have a small dimension, then you cannot, like if you have this upper bound of the dimension, you can use it to estimate how many such sets you have. So this type of result is kind of like, it pops up in other places, and you could have used this one also for what they are doing, but they have a nice proof of their own, which is getting kind of some similar ideas, but they're just doing counting rather than dimensions, so it's a bit easier, and they're getting better bounds, which is harder. So, but it's a nice, very, very nice result, still coming as far as I'm aware of. Very good. So I promised a proof of the corollary. Right. So what's the setup? So let S be maximum dissociated subset of A. Right, so the size of S is just the dimension of A. This is the definition. And let's build an auxiliary graph. So consider an auxiliary graph with vertex set being just a disjoint union of A and A times A. This is my notation for a disjoint union. So you just take a set consisting of vertices in A, of elements of A, and a disjoint copy of elements in A times A. And then for the edge set, it's just going to be all the pairs where the first one is A and the second one is A times S, where A is an element of A and S is an element of this maximal dissociated subset. Right? So it's some form of bi-Cayley graph. So yeah, you put an edge between A and AS. So I guess I should do something like that. And very good. So now note that this also gives a kind of natural coloring. So this gives rise natural coloring, namely A and A times S will be colored in color corresponding to S. Small s. Right, so this edge just goes from A to A times S, so we give it the color of S. Very good. So, so this is a proper coloring, right? Just by the group properties, so you cannot go from A, like if you go from A and to anything else, you go by a different element, so you are getting a different color. So the number of vertices is at most the size of A plus the size of A times A, which we are assuming is at most K plus 1 times the size of A. Right, so roughly size of A many vertices. So, yeah. And what's the number of edges? Well, it's just the size of A times the size of S, because you can choose A and then you can choose any element of S. Very good. So we also know that there is no rainbow cycle. And why is that? Well, suppose you have one, and if you trace it, you get colors S1, S2 inverse, S3, S4 inverse, right? So you are in this bipartite graph, and you are just following some kind of cycle here. So this was in color S1, this was in color S2. We're going back, so we need to multiply by the inverse, but the color is S2. So this is S3, and then S4 inverse, and so on. Right, so if you had a cycle, that means you end up in the identity. So whatever this A was, you actually had A there, and you had A here, so you can cancel it out. So what you just got is a non-trivial linear combination of distinct elements, right? So these are all distinct elements that live in S, and we assume that S is dissociated. So that's a contradiction. That's not possible. So we don't have rainbow cycle. So now you can just use our bound on the Turan number, and this tells you that like the size of A times S, which is just the size of A times the dimension of A, right? Because the size of S is the dimension, is at most big O of number of the number of vertices, which is just something like K times the size of A, times the log number of vertices, which now you can just replace with the size of A, times log size of A, which is precisely what I claimed you get. So in some sense, it's a quite natural way of trying to break these dissociated sets. And the same type of idea actually pops up in some other places. So we have also some geometry applications in mind that we are doing with this type of thing. But I'll not go more into that. So any questions about that? Good. So in the last 10-15 minutes, let me tell you a little bit about how this rainbow cycle result is actually proved. So, as you might have guessed based on the timeline, I will not really have enough time to tell you the whole proof, and not even a proper sketch, I'm afraid, but I can tell you like some kind of high-level overview of what's going on. So, as I said already, the main idea is this pass to the expander approach, which was pioneered by Komlosh and Semeredy some 30 years ago, and then developed quite a bit and used to do great stuff by, in large part, Hong and also Richard Montgomery and a few other people over the years. So it's quite a powerful tool that has found some nice applications recently. And every paper that is doing this is kind of tweaking the definition. So let me stick with the tradition and tweak the definition and kind of make it slightly stronger, more applicable to what we're working with. But I think it's quite nice, and it kind of really captures somehow the best you can do with these sublinear expanders, at least if you're living in the world where the density is about log n. So also what I should say before telling you the definition, that the point of these expanders and the reason we look at them and they're useful is that in an arbitrary graph you can find a this sublinear expander, so a weak notion of expander, which actually has roughly the same average degree. So you just lose a tiny bit in the average degree, and you get your expander subgraph. So if you're looking at a question like this, in which we really care about the only, well, it's no longer, the definition is no longer stated, but we only care about what amount of average degree you need in order to guarantee a structure, this tells you that for free you can just assume your graph is one of these expanders, and then just carry out the whole proof working inside of that expander. So that's really the kind of key idea behind them, and what the reason why they were so useful over the years. So an n-vertex graph, definition, an n-vertex graph, H is said to be robust, sublinear expander. And this robustness is a kind of new tweak that actually appeared in some form in the paper of Hasselgrove, Kim, and Liu, and then was tweaked by myself and Richard when we were working on this Erdős-Gallai conjecture. And this is a kind of evolution of this type of tweaks. And let me finish the definition. So it's a robust sublinear expander if for every epsilon which is bigger than 0, so that actually bigger or equal than 0 and at most 1. So this, don't worry too much about it, it's just here to control the size of the set. You'll see in a moment what its role is. But the point is that every subset of your vertices should have reasonably big neighborhoods. So for every subset of the vertices, such that its size is at least, at most, n to the 1 minus epsilon. So this is the role of epsilon, kind of, to tell you how big this set U is. And I'm putting at most n to the 1 minus epsilon here, so I don't need to do floors and seals. But you should think of it as just saying equal, essentially. Because the smaller it is, the stronger the expansion you will be having. So there is a final bit, which is what gives you the robustness, and I'll draw a picture. But you also are given a set of edges that somehow your worst enemy is giving to you, and is restricted that they should not be too big, so they should have at most size epsilon times the average degree of your graph times the size, like epsilon times the average degree of the graph over 3. And I am missing the size of U. Yes, I am. And the conclusion is that the size of the neighborhood, if I forbid you the use of these edges, when you expand this subset, should be at least epsilon times the size of U. And let me put 3 here so that it's actually correct. And we're going to use it. So let me draw a picture. So here's our would-be expander. Here's our subset. Epsilon is just controlling how big it is. And now your worst enemy comes and tells you you cannot use these edges. Okay? So these are bad. No. So instead of that, you can use, like, you still have maybe some edges left. And if you look what you can reach in one step going out of U, this tells you that you should still get a kind of sensible amount of vertices here. You should still see some amount of new vertices, even despite the forbidden edges. Okay? So what's this epsilon stuff here? So if epsilon is an actual absolute constant, then it tells you that any kind of subset which is polynomially smaller than linear expands by an actual constant factor here, right? But you can also plug in epsilon to be something like 1 over log n, so that you can also expand sets which are linear in size, so almost everything. And what you're getting then is that the expansion is no longer linear, it's something like 1 over log n times the size of the set. So this is why it's called sublinear expansion. And this type of epsilon thing is just making a relatively clean statement of how much expansion you should expect of sets of different sizes. And in order to get this kind of relatively tight, super tight result from the perspective of expanders, you really need to do this kind of careful intermediate control of how various sets expand. And the reason for that is that if you do a quick computation, you can see that the diameter of this graph is roughly log n log log n. So how do you prove the diameter bound in an expander? Well, you just start from two vertices and like you first expand around one. So long as these sets are small, they will expand by a constant factor. But once they become kind of bigger, or say around linear size, now they're only expanding by a factor of 1 plus 1 over log n in a step. So if you do the computation, like if it was always 1 over log n, if you were careless, you would get diameter bound of log squared. So once you reach more than half of the vertices, you can play the same game from the other side until this is also bigger than n over 2. Right, and then you have a path that like has length however many times you need it to expand until you kind of join the two paths from two vertices. And these were arbitrary, so that gives you a bound on the diameter. So this is standard way you bound the diameter in any expander. So here it's just that the diameter bound, the computation is a tiny bit unpleasant because there is this varying thing, but you kind of do it in cloud. It's not too hard, but it turns out to be log n log log n, and this is really kind of the reason why we cannot improve this log n log log n with the approach that we're doing. Very good. So now the point of usage of this, of like how you are supposed to use this thing. So here's a lemma, and the lemma says that in any graph G, there exists a robust sublinear expander subgraph H such that the average degree of H is at least log the number of vertices of H, sorry, log the number of vertices of H divided by log the number of vertices of G by 3 times the average degree of G. So what this is telling you is that you have an arbitrary graph. You can find one of these expander subgraphs which have average degree roughly the same as the average degree of your original graph, so long as this is at least log. Right? So if you are working with a graph which has average degree at least log, then this log and this log cancel, so you're still getting an average degree of roughly log from the perspective of H. So it's a relative average degree, right? It might shrink if these graphs might be small when you're passing into it, but you're still getting, and this you can tweak in various ways depending on what density you're working with, but when you're working with log, this is a nice clean thing that you get out of this. And the rough, nice idea how to find this is that you just, if you take H to maximize the average degree of H over the log number of vertices in H minus some kind of correction factor, which I'm not going to explain why. But essentially, you want to find the densest spot in a certain non-obvious relative way. So the density you're looking at is the average degree divided by the log number of vertices. And this is a kind of nice one-step way of finding these expanders. You can also use the standard find the sparsest cuts, look at left or right, and repeat inside of left or right. This kind of just in one step gets you the same thing that this process usually does. So I am slowly running out of time, or maybe even ran out of time. So let me just maybe say one word, one quick sentence of just to give you a rough idea of why these things are useful for finding this rainbow cycle problem, So the general idea for how we are going to find the rainbow cycle is going to be that we are going to subsample colors with probability half, left and right, and then just expand in our expander by using only the first half of the colors, and then expand using the second half of the colors. And then, like, if you can reach more than half of the vertices with some bigger than half probability, then you get some kind of walk there and then a walk back. And this is using different colors. And if you are always expanding in a certain rainbow way, that will give you a rainbow closed walk, so a rainbow cycle as well. This is a bit fast, but the general idea is that you will still play a similar game as there. You will expand that, but you need to work much harder because you need to ensure when you're doing this expansion thing that every vertex is reachable by a rainbow path, and I want it to be reachable by somehow the set of colors, the set of like a random subset of the colors, which we are sampling with probability half. So both of these things are kind of problematic if you try to run them, but just to give you a little bit of a picture of why this, where this like F part, so why these red edges, like forbidden edges, are nice. So suppose that we are not subsampling colors. You can easily actually tweak that and get a proof of log squared log n in just a few more steps once you have these type of expanders. So what you do is you're just doing a rainbow expansion. So I look at a set that I can in one step reach using rainbow colors, so that's just the neighborhood. Then vertices that I can reach in 2 steps using rainbow paths, 3 steps, and so on. And I want to reach more than half of the graph. And so the point is, at some point you have a set of vertices which are rainbow reachable. So they have some path that was rainbow that reached this vertex. So that means that when you try to expand this new set, you have some forbidden edges, right? If this one has a red edge going out, you're not allowed to use it to expand. And this is precisely where this type of forbidden edges are going to come in, right? So there are some collection of edges which you're not allowed to use when you're expanding. And if you have that, otherwise you still expand, that's good. We can grow exactly in the same way. Because this thing is telling you, even if I forbid you some decent amount of edges, I can still expand. So that's precisely what's going on here, except that what is a decent number, so if this epsilon is something like 1 over log n, and the average degree is log n, then you're getting here just the size of u times log n. So you would like to expand here by, so you only have maybe, like, you're only allowed to forbid roughly log n edges per vertex in this subset on the left, and you would still want to expand. But your paths, because the diameter is roughly log n, might be of length log n. So you get a log n times log n forbidden edges going out of this vertex. So you cannot do it. But if you put log squared there, then everything works out magically. This problem goes away. You get a very short proof of log squared and log n. Just that and the 2 more steps. So one needs to be this subsampling trick. Like, how do you get this also that you are using a random set of colors? But that gives you a kind of nice clean proof of log squared and log n. And it also somehow showcases why getting this log n was so hard. Because in some sense here, like, this is way too weak. And in a sense, what saves us is a kind of clever way that if you actually have a lot of edges here which are forbidden, then you can say in some sense that, like, all the colors that you see here, so suppose that all of these things are forbidden for him going out. That's a bit bad picture, but anyway. Then any path from here to here needs to use all of these colors. And now, because we are subsampling these colors in each step, which I didn't really explain much about, but what it's telling you is that in the previous step, if a lot of things are blocked, then this vertex was just added. So it's a very new thing. So somehow, like, you will be expanding in stages, so slowly growing this thing. And if the vertex here has a lot of blocked things, it means that it's like every connection from the start to here needed to use all of these colors. So somehow when you looked back, here you sample the color randomly, So the probability that you hit one of them is actually pretty high. And as soon as you hit it, it's disconnected from the previous one. Because all the paths that go from here to here needed to use all of these colors. So, I mean, this was very fast, and I would need some more amount of time to explain what is going on here. But that is really kind of the key perspective that lets you still win, even if you are at density which is much weaker, so that you cannot run the usual type of just forbidden stuff there. Let me stop there, and sorry for running a bit over time.
Any questions?
Can we apply the similar methods to get a better bound for rainbow KT subdivision?
Yeah, so that's a very good question that I was asked in a few places. So as far as I know, no, but like I don't, I mean, so it's quite possible that you can tweak something and do it, like directly as we're doing it, it will not work. So somehow, like, so actually this, like, it gives also this log squared log n argument that I told you. It actually gives a very short proof of the subdivision as well. So the same log squared and log n that is still, I think, best there. You are not getting the subdivision with the log squared n, right? So so that yeah. So somehow.
Well, the question is, do you think it's interesting?
I think it's interesting mostly because like it would force you to do maybe a slightly better variant of this argument. So, so yeah, and I mean, it's a nice problem. So, like, we thought a tiny bit whether we can tweak the argument, and there are several kind of problems that you run into when you try to do this. And somehow, like, this nice way of doing like this forbidden edges is actually perfect for finding subdivisions. But you again run into trouble that you don't have enough forbidden edges to do it, because for the subdivision you can just build it greedily. You build a part of it, like, I don't know, let's say 3 of them, you build these parts of it. So you now just, like, these parts will be of length log n, so you just forbid all of these vertices. And this will only ever forbid you a log times log n or whatever colors from any set that you expand. So you can just kind of expand while ignoring whatever was happening here, and then just join these two vertices. And like finding a cycle is exactly, like, it's exactly the same argument that gives you the subdivision for log squared n. So that's a kind of also shorter, nicer tweak. So there is this best result there is due to Wang. I didn't mention it. There is a parallel pole universe of results for the subdivisions which were trailing these. And I think it would be quite nice to get that. But there are several issues if you try to run this thing. I mean, I didn't say enough that it would make sense to go explain it. But I can tell you later if you're interested. At least some stuff.
Thank you.
Thank you for the question.
Other questions? Okay, maybe, well, Matija will be with us for a couple of days. If you have other questions, feel free to chat with him. And let's thank Matija again for the excellent talk.